computer forgot that I didn't capture the screen recording software. I went down and got the other laptop. So this is if you missed class or whatever, you can go back and watch the video. Other students have found it helpful that if they missed something in class, they can go back to the video and go back and listen to it again. Okay. So that's why I record it. I will post a link to it on Moodle. Usually I post it on YouTube. And then I'll just post a link so you can go connect, click directly to it, link directly to it. So in any event, let's get started in this stuff. So this first section, we talk about different properties. Oh, my ink is a different color. Go away. Or don't go away. Just stay there. That's fine. Go back to blue. Black. So our first section, 1.1, talks about properties of probability. So, of course, this entire course is about probability. But we want to start with a set of, I'll say, accepted truths, for lack of a better word. But we'll start with a set of accepted truths that we want probabilities to have, and then we'll talk about different scenarios where those truths apply. So when we talk about accepted truths, we usually refer to those as axioms. So we'll have probability axioms that we'll talk about here in a minute. What we'll want to think of is what kind of things that we want these properties to have before we start setting those axioms. So before we get to that point, there are some connections between probability and what's referred to as set theory. Some of you have had discrete math, some of you have not had discrete math, so we'll just keep the set theory to a minimum. And when you take discrete, if you take discrete, but when you take discrete, you'll get into it a little bit more in depth. So for our purposes, we can just think of a set as just any collection of objects. Doesn't matter what those collections are. It could be what we refer to as a discrete set. By a discrete set, we mean there's not really any connections between the elements. So for example, if you use the counting numbers, 1, 2, 3, 4, etc., that is a discrete set because there's not really a connection from 1 to 2, right? There's not continuously connected, if you will, right? There's a 1, then there's a 2, then there's a 3, and so on. That's an example of a discrete set. Versus a continuous set would be, say, all the real numbers between 1 and 2. Those are really connected through all the decimals and all the fractions and all those things in between. Okay. That's the difference between a discrete and a continuous set. So we will talk about probabilities on both of those types of sets later on. But just to mention, like I said, just a little bit of set theory. Sets a collection of objects, and you should understand what the definition of discrete versus continuous is. Not much more in depth than that. All right, so when we talk about probabilities, we are talking about, you think about probabilities, think about the chances something happens. Well, the first thing you need to do is start generating cases of what happens versus what doesn't. So one of the simplest examples you'll get from a probability standpoint is talking about, say, flipping a coin one time, right? Okay. Two possible outcomes. It could either land heads or land tails, assuming it doesn't magically land on its edge. So we get those two possibilities. But you can start thinking about more advanced outcomes. Like, for example, if you take a six-sided die and roll it one time, well, then you've got outcomes that could be 1, 2, 3, 4, 5, or 6. Right? More complicated scenarios, the more complicated there are for outcomes, right? Maybe you flip the coin and roll the die at the same time. Right? So then you can do like heads in 1, heads in 2, and so on the line, right? Those kind of things. But start thinking more advanced examples. If you want something, all those examples I gave you were discrete. Just then, you can think of more along the lines of maybe you've got a circuit and you want to know the time until it fails. What's the probability it fails within an hour or lasts longer than 2 hours or what have you? That's more of a continuous idea. So in any event, all of those things are doing outcomes of something happening. That something happening idea is what we refer to as an experiment. All right. So as far as we want to talk about is it's just an experiment is just any outcome that we can measure, that we can observe, I guess I should say. If you could spell the word observe, that would be helpful. And now my pen stopped working. There it goes. What are you doing? Spell, be observed, and recorded, I guess I should say. That's all we mean by an experiment. Kind of coincides with your idea of doing a scientific experiment, right? You do something, you see what happens, you record what happens, right? One of the things that's important in science is to be able to replicate an experiment, right? Just because somebody does an experiment and gets an outcome, you might replicate it and see if you get the same outcome, right? Okay. Same idea here. When we do an experiment, we might do that experiment over and over and over and over and over again, right? Flip a coin, flip a coin, flip a coin, flip a coin, do it over and over again, right? Roll a die, roll a die, roll a die, do it over and over again. So same kind of idea. We want our experiments to be random, meaning that whatever happens isn't predetermined. Now, there might be different chances of something happening versus something else. For example, if you roll a die one time, the chances that you get a 1 versus don't get a 1, different, right? Okay. So the chances of the same an outcome happening doesn't have to be the same for every single outcome. However, we don't want it predetermined ahead of time, right? For example, you don't want to load a die, right? See, I'd say like, so we want random experiments as we're going along. So when you think about doing the experiment and think about all the different ways that you can get an outcome, we refer to that as the sample space. So the sample space of an experiment, oops, is a set of all possible outcomes. That's going to depend on two things. One is what the experiment is, and two is what are you looking for, right? What I mean by that is you could roll two dice. Maybe the outcome that you want is the sum of the two dice, which is if you play board games, that's what you typically do, right? If you roll two dice, you're looking to do the sum of those two dice. But that may not be the only thing you want to do, but maybe still roll the same two dice. Maybe you roll the two dice and you ask what's the product rather than the sum. That's the same two dice, but a different outcome, right? Yeah. So depending on what the experiment is, will generate what your sample space is, right? But again, you may use the same object, but looking for a different outcome. So like I said, it's whatever the experiment is and what outcome you're looking for. So that's what we mean by the sample space. If you've done anything with sets, you might think of sample space as coinciding with a universal set. The set of all elements under discussion is a universal set. So if you've done discrete, you might have talked about universal sets. Sample space is playing the role of universal set here, probability. All right, so the sample space is all of your possible outcomes. When we're talking about an event, something that happens, we refer to that as an event. And if we think about sets and subsets, an event is just a subset of the sample space. So we'll talk a lot about events. As a matter of fact, I'm writing here along where I've got the problems embedded on the screen. But notice here, This particular problem they've got, I think it's probably the first one on your page there. It says you've got an 8-sided die rolled once. And you're going to record the outcome. Okay. If I were looking at that 8-sided die rolled one time, what would your sample space be? 1 through 8, right? A lot of times you'll use the letter S to denote sample space. And your sample space would just be the number is the integer is 1 through 8. Discrete set or continuous set? Discrete, right? Because it's 1, then 2, then 3, right? If you think about it, maybe you think about plotting things on a number line, you would plot those with individual dots on the number line, right? They're not connected to each other. That's what makes it discrete. Right? The number line itself would be continuous, but the dots are separated from each other. That's what makes it a discrete set. Does that make sense? All right. So that would be our sample space. Then notice that they've got, in this problem, and we're not going to do this problem right this second because we still want to talk about finding probabilities. But notice that they've got 4 other sets listed for you there. Notice that all of those sets are subsets of your sample space, right? Every element in one of those sets is also an element of the sample space. That's what makes it a subset, right? Everything in A is included in S, so A is a subset of S. Right. Notice that we call all those events, right? There's an event A, an event B, an event C, and an event D. They've got listed here. Okay. The symbol that we use for subset is this one. It's supposed to make you think of less than or equal to. So this is the symbol. So it looks like an elongated C with a little equal sign, like the bottom half of an equal sign underneath it. So again, it's to think of less than or equal to. So the whole point of the notation. Again, what we mean for subset is if something is an element of A, then it's also an element of B. So to introduce that symbol as well, we use, again, you may be familiar with these, and maybe I'll be telling you what you're going to do. Just want to make sure we're on the same page with notation. This is an element symbol. Means that something is in the set. So for example, up here, I would say 2 is an element of S. If something's not in there, then just like when you do not equal to, you put a line through it. So the number 9 is not an element of S. Again, the only reason why I'm going through this is because I want to make sure that we have all the notation all set for everybody because we're going to use it all semester. Some books, and I think our book actually, sometimes they don't put the little equal to sign here for subset symbol. I do because there's also another notion of what we refer to as a proper subset. Means that it's like strictly less than. Okay. Every element of A is also an element of B, and they're not the same set. So B actually is bigger in some sense, right? There's something in B that's not in A. That's what we mean by proper subset. Sometimes for emphasis, if you really want to make sure that you're saying proper subset, sometimes you'll see books will do that. Just emphasize that it's not equal to. Okay. Anyway. So just like I said, I just want to make sure that we've got these ideas down. as far as what we mean by these things. Because again, when we describe what an event is, an event has to be a subset of the sample space. Going back to this problem, I don't think, notice that none of the A, B, or C, or D are subsets of the others, right? There's always something that's in one of them that's not in any of the others, necessarily. So, or in the other, I should say, from any pair that you pick. So, for example, if I look at the set 3, 6, it's not a subset of D, even though 3's in there, 6 isn't, for example. So none of those are subsets of any of the other ones except for the sample space. Now, there are a couple of instances that I will mention that are kind of interesting. Notice that those two sets don't have anything in common, right? Also notice that these two sets don't have anything in common, okay? So if I want to talk about the things that are the set of things that are in common, we refer to that as the intersection. The intersection of two sets is the set of elements in both sets at the same time. The notation for intersection is like this upside down U. A lot of times if we think about doing an English translation of math, intersection is the same thing as and. You can think of it as a set of everything that's in A and B. Or if you've done some logic things, and an intersection are the same idea. And we'll do an example here in a second of what we mean by intersection, make sure we're okay with that. The other notion that we have besides intersection is the idea of union. If intersection is and, then union is or, okay? So this is the set of elements in in one or the other set, or both. It could be in both at the same time. It's in one or the other or both, and the notation we use for that is a U. So going back over to our example, one of the things it's going to ask us, notice in some of these parts, is looking for probabilities of intersections and unions, which we'll talk about how to do here in a little bit. But if I want to do A intersect B, this is the same. This is the set of everything that's in both A and B at the same time. What is the intersection of A and B? 6, right? So it would just be the set containing 6. That's the only element that's in both A and B at the same time. What if I want to do the union instead? Well, that's in one or the other, or both. So what's that going to be? 2, 3, 4, 6, 8. 2, 4, 6, and 8 are in there because they're in A. 3 is also in there because it's in B, and it doesn't matter if the 6 is in both of them, it's still in the union. One of the good things about sets is that it doesn't, the order that you list things in doesn't matter, right? So if you would have just done, if you say you wanted to do a union and you did the set A first and then threw in the things that were in B that weren't in A to start with, that's the same answer. Does that make sense? Okay. So that's intersection, that's union. Notice one of the other things it asks us about is intersection of B and C. That's going to be one of the probabilities it asks us for. But what did we just say about B and C? Do they have anything in common? No. So if they don't have anything in common, we use a special symbol for that. Whoops. It looks like a 0 with a line through it. It's actually, I believe, a Danish O, if I remember correctly. But um, that's the symbol we use. It looks like a 0 with a line through it. We refer to that as the empty set or the null set. It's the set with no elements in it. And we're going to have and for probability, we're going to have a special name for this situation. Pardon me. But that's what we mean by the empty set. Notice that by definition, the empty set is a subset of every single set. Because remember, our definition for subset is if it's in the first, then it's in the second. To show that something's not a subset, you'd have to find something in the first that's not in the second. Can I find any elements that are in an empty set? No. So we refer to that as a vacuously true statement. The empty set is a subset of every set because it's impossible for it to be false. If it's impossible for it to be false, it has to be true. That's what vacuously true means. Okay. Fun words today, you know. Sometimes the first days of learning something new are boring as all get out because all you get is a bunch of definitions. Maybe you find it boring all the time, but a lot of times when you're first learning something, it's pretty boring and all you have to learn all the definitions to start with. Anyway, from a probability standpoint, when we have two sets that have empty intersection, we say that B and C are mutually exclusive. Standpoint, this would mean that the two events cannot occur at the same time. So to give an example, maybe your events are, for say we roll a die. Okay? Maybe event A is roll an even number, event B is roll an odd number. Those are mutually exclusive. I cannot roll an even and an odd on the same roll. Right? It has to be one or the other. Okay? Versus, I say event A is roll an even number, and event B is roll a multiple of 3. Those are not mutually exclusive because I can roll a 6, which is even and a multiple of 3 at the same time. Okay? So that's an example of events that are not mutually exclusive. They have some intersection. Does that make sense? All right. All right. A lot of definitions, I know. All right. So let's talk a little bit about some properties that we want probabilities to have. Okay. So these are going to be what we refer to as our probability axioms. Your book lists this as definition 1.1-1. I'm not going to write all those numbers. All right. So what do we mean by a probability? All right. So we're going to let S be a set. And let A be any subset of S. A function, and I'm going to use some other notation here. I'll tell you what it means here in a second. A function, I'll call it little p, from what we refer to as the power set of S to the interval 0, 1. Okay. I'm going to come back to this in a second. Let me just write out the next part of the sentence, and then I'll come back and describe what this set means. Is called a probability function if, and I'll get to the if part here in a second. Again, many of you may not be just familiar with discrete, so I need to define a couple of things for you, but we're only going to define it for a second, and then I'm not going to care if you remember it. Okay? This is a pretty common notation for describing a function. This is just telling me what the inputs are, what the domain is. This is just telling me what the codomain is, what the outputs, where the outputs live. Okay? This fancy script P stands for the power set of a set. Power set is just the set of all subsets of a set. We just said that the sample space is all possible outcomes, and an event is a subset of the sample space. So all I'm defining is a function that has a domain of all possible events. Right? Events have to be subsets. Okay? This is just a fancy notation for it. I don't really care that you know it past that. Okay? All you need to remember is an input is an event, an output is a number between 0 and 1. Okay? That's all you literally need to remember. Okay? An input is an event, an output is a number between 0 and 1. Which makes sense if you think about probabilities, right? You usually think about them as percentages. Can anything have a less than 0% chance of happening? No. Can anything have a greater than 100% chance of happening? No. Okay. So it makes sense that it would be between 0 and 1, right? So again, I know it's a new notation maybe for some of you. I don't really care about the notation. Just you're going to put in an event and get out a number between 0 and 1. That's all it's saying. Okay? All right. Well, what do we want this to be true? Okay. Well, I already have defined it this way, but the book also makes sure that it emphasizes this. That when you do the probability of an event, it always has to be greater than or equal to 0. The way I have this written, this is redundant, right? Because I just said you put in an event, you get something between 0 and 1. Okay? But just to emphasize that we really do have, you cannot have a probability that's less than 0. The second says, what happens if you put in the sample space? Don't know why this thing is having issues. It says, what happens if you put in the sample space? Well, again, remember, nothing can have a probability greater than 1, 100% chance of happening. The sample space is the whole space. If you run an experiment, what's the likelihood that you land in the sample space? It's 100%, right? You have to land in there. So the probability of the entire space is always 1. The third one has to do with this mutually exclusive idea, right? So if you have if A1, A2, A, and so on are mutually exclusive, or I'll say pairwise mutually exclusive, then the probability function has a special property. Let me talk about what I mean by pairwise mutually exclusive. Pardon me. What I mean by that is if I take any of the A's and do the intersection with any of the other A's, I get the empty set. So if I take any two of them, distinct, if I take any two of them and look at their intersection, it's empty. Okay, there is no overlap between any of them. Okay, so if I take pairwise mutually exclusive events, then our probability function, of the union and it can be an infinite union, doesn't have to be a finite union, will be the sum of the probabilities of each one. Oh, I wrote a K instead of an N like I did before. This defines a probability function. So probabilities are always non-negative. They're never bigger than 1. And if I do the probability of a union of mutually exclusive events, then it breaks up over the union as a sum. Now, being mutually exclusive is very important, and we'll see that here in a second. Okay. All right, so let's go back to this first example and see if we can apply this. All right, so going back up to this example where I've got stuff written all over the place now. Okay. A fair 8-sided die is rolled once. Pardon me. Means we have 8 possible outcomes. Since it says the word fair, that fair means that each face is just as likely to pop up as every other face. That's what it means by be a fair die. Okay? A loaded die would mean that one or more of them have a different probability than the other ones. Okay? So if there are 8 possible outcomes and or 8 possible numbers, and you're going to roll the die 1 time, that should mean that every single one has a probability of 1 out of 8, right? Okay. So notice that we look at, pardon me, the probability of the event happening is the probability of an event in this case is going to be how many ways the event can happen over the number of ways the sample space can happen. This absolute value bars stand for cardinality. It's number of elements in a set. Okay. In the next section, we're going to talk about different counting methods and how many ways, how to figure out how many ways something can happen. And since we have a fair die here, all the outcomes are equally likely, so we should be able to count these things pretty quickly. In the problem, it said that our event A was the evens, right? 2 through 2, 4, 6, 8. Is that right? Okay. So using this definition, the probability that A can happen, there's 4 elements in A and 8 in our sample space. So we would get 1/2 for that, which makes sense, right? Because A has half the size of the entire sample space, and every outcome is equally likely. You can do the same thing for the other ones, right? What's your probability of B going to be? You get 1/4, right? It was 2 out of 8 because there's 2 elements in B. And we can reduce it for C. Creates. Good. And for D. Yeah, 1/2 again is 4 out of 8, right? So it's all good? That was the first part? The other ones, part 2 was looking for the intersections. I need to scroll so I can see what the problem is. Intersections in A and B, B and C, C and D. All right, so let me just write down the sets are again so I don't have to keep scrolling. And I just wrote down the wrong set. B was 3, 6. C was 2, 5, 7. Is that right? And D was the odds. So the first one asks for the probability of A and B, probability of A intersect B. What's the denominator? No matter what problem we're doing here, what's the denominator going to be? 8. Good, because there's 8 possible outcomes. Good. All right. If we look at A and B, what do we get? How many elements are in the intersection? Just one, right? So our numerator here would be 1. And again, we can see that because we said the intersection of A and B was just the element 6, right? We also talked about B intersect C. What was the intersection of B and C? Empty set, right? So how many elements are in the intersection? If it's the empty set, how many elements are in there? 0. So what's the probability going to be? 0. Good. If the probability, and that should happen for any intersection of mutually exclusive events. The intersection should, the probability should be 0. So it means for being mutually exclusive. A probability of 0 is referred to as an impossible event. That event cannot happen. Okay. If they're mutually exclusive, that means that the two events cannot happen at the same time. So they would have a probability of 0. The table there. And finally, for C and D, intersection of C and D, what do you get? 1/4 again? Because the intersection is 5, 7. There's 2 elements in there. So we get 1/4. That okay? All right. The last part wants you to do unions. Now notice that in our definition for union, it says if they're pairwise mutually exclusive, then I can break it up over a union as a sum, right? So for example, if I look at B and C here, those are definitely mutually exclusive, right? So I'm with the probability of B union C, I can just do the probability of B plus the probability of C. Because they're usually exclusive, right? So in this case, you would have what? 1/4 plus 3/8 and get 5/8. Assuming I added my fractions correctly. Never believed my arithmetic on the first try. Yes.
So when we use that, when we asked put into definition,
Say that again.
when we use that method, when we're asked to put into definition.
We will use this method quite often, actually. We would, but we can only ignore the we can only do it this way if the intersection is empty. We'll talk about it, what happens if it's not empty here in a second. Yeah. But we can as long as we have a union, we can always do it this way if they're mutually exclusive, and we'll actually use that a lot. Okay. Okay. Notice that, however, if I do the probability of A union B, are A and B mutually exclusive? No. And notice that in this case, if I try just to add them, put a question mark over that. Notice we already said that A union B had 5 elements in it, right? A and B had probabilities of 1/2 and 1/4. That gives me 3/4. Are those the same? No, that doesn't work, right? Okay. So what happened? Well, again, if you've had discrete, you might already know what happened. Okay? Doing the probability of A basically counts everything in A. Doing the probability of B basically counts everything in B. What did I count twice? 6. Yeah, I counted the 6 twice, right? In that, I counted everything that's in both 2 times, okay? So the result that we actually want to do, and this is a theorem, the probability of A union B is always the probability of A plus the probability of B minus the probability of their intersection. Always. And again, if you think about it from a counting perspective, it makes sense. In some sense, this probability counts everything in A. This probability counts everything in B. You've counted everything in both of them twice, so I need to subtract 1 copy off. That make sense? Okay. All right. So that we can actually use to help us do some of the other problems. Notice over here, I could do the same thing with this. Your probability of A union B will be probability of A plus probability of B minus the probability of their intersection. And I would have 1/2 plus a 4th. Their intersection has a probability of an 1/8 happening. And you really do get the 5/8 in that case. Now, this is such a simple example, we could have just counted the number of elements in union B to start with, but I just wanted to do this for illustration purposes. These concepts making sense okay so far? Not too bad? All right. Let's talk about one more concept that pops up on your next page in the next problem. Notice they introduced a new notation for you here. They got this little tick mark, this little apostrophe, this little prime notation next to a cell. That notation is the notation for the complement of the set. Okay, so if I do A prime means the complement of A. This is the set of everything not in A. It's the complement. You may be familiar with a different notation for complement. Other notations for complements are bars over the top, or maybe a superscripted C. We will stick with the prime notation because that's what your book uses, but know that other books might use other notations. In particular, the bar notation over the top is just as common as the prime notation. The C notation is a little less common, but it does appear. But we will use the prime. Okay? All right. How do we do the probability of a complement? Well, we can do that by thinking about what the probability of an entire space is. What do we say the probability of an entire space is? 1. Good. Well, one way to write your entire space is take an event and union it with the complement of the event. Well, think about it. Either something is in a set or it's not in a set, right? Those are the only 2 possibilities. So if I take any event A and union any complement of that same event, I have to get the entire sample space. Because either you're in the event or you're not, right? Now, does a set and its complement have anything in common? Do they have any intersection? No, because again, one's the set of things that are in there, one's the set of everything that's not in there, right? So an event and its complement are mutually exclusive. What can you do with a probability function? How can you rewrite the probability function of a union of mutually exclusive events? How can I rewrite the left-hand side of that equation if they're mutually exclusive? Good. Right? If they're mutually exclusive, you can change the union into a sum, right? And we know these don't have anything in common, so I can break it apart. And now I can solve for the probability of A complement. And trust me, this is a helpful property to have, because a lot of times it's easier to calculate the probability that something can't happen versus the probability that it can. Let me give you an example. I flip a coin 8 times. What's the probability of I get at least heads one time? Well, at least heads one time means it's 1 or 2 or 3 or 4 or 5 or 6 or 7. That's a lot of counting, isn't it? But think about what's the complement, what's the opposite of at least one? None, right? I can calculate the probability of no heads pretty quickly, because no heads means all tails, right? There's only one way to get all tails, right? It has to be tails on the first and the second and the third and the fourth, right? I can do that a lot more quickly and then just subtract it from one when I'm done, okay? So this probability of a complement idea is going to help us later on a lot for calculating probabilities. When it's harder to do it directly, we can get it indirectly a little bit more quickly. So this is a theorem. This is always true, okay? So going back up to the example, although we haven't done any of these parts yet, if I look at probability of A was 0.4, what's the probability of A prime going to be? Yeah, 1 minus the 0.4, good. So it'll be 0.6. If your probability of B is 0.5, then your probability of B prime will also be 0.5, right? Does that make sense? All right. So let's see if we can use that plus the properties that we came up with before to answer these other questions, okay? So if you want probability of A union B, by the way, looking at what, pardon me, looking at what they gave you, first question let me ask you, are A and B mutually exclusive? By the information they gave you. No, how do you know not?
Because their probability is 0.3.
Good, good. The probability of the intersection is 0.3, so they're not mutually exclusive, right? The probability of the intersection would have to be what if they're going to be mutually exclusive? 0. Good, good. All right, so these are not mutually exclusive. So if I want to use the formula we came up with earlier, how would I rewrite probability of A union B to start with?
Probability of A is probability of B minus probability of C.
Probability of B minus probability of the intersection. And now we know numbers for each of these, don't we? Probability of A is 0.4, B is 0.5, A intersect B is 0.3. Little arithmetic tells us that's 0.6. You can do something similar for C. You're just going to use the A complement and the B complement, except that you also need to know what the probability of their intersection is going to be, which we'll talk about in a second. Let's talk about how we would do B. And I think a picture might help for B to start with to see what's going on. Okay. One way to represent sets and their interactions is what's referred to as a Venn diagram. You may have seen Venn diagrams before. So let's say I want to talk about how A and B might interact. Don't draw the first ones down, just draw the very last one here in a second, okay? What if I drew A and B this way? So A and B are representing sets, and I don't make them overlap. What situation do you think I'm representing here pictorially? Mutually exclusive, right? They don't have anything in common? Good. What if, and this is why I said don't write it down because I'm going to start erasing things, so I'm going to draw 8,000 pictures, okay? What if I did, whoa, that was fun. What if I did, why do you stop doing that? This. What would that represent? Yeah, B is a subset of A, right? Drawing it that way inside. Of course, I could draw B as the bigger circle and do it the other way around, right? But ordinarily, if you're thinking about sets and their interactions, usually you think of them having a little bit of overlap, right? Agree with that? Okay, cool. All right, so this region right here would represent what? The intersection of these two things, right? Cool. All right. So in our scenario, if I think about labeling this region, this is kind of helpful sometimes to label these regions with numbers, either probabilities or actual honest to goodness numbers. I could label this with a 0.3, right? Because they tell us that the intersection of those two sets is 0.3 in this scenario. Okay. In this entire circle for A, how big is it supposed to be? What did they tell you the probability of A is? It's 0.4, right? We've already accounted for 0.3. So what do you think we could fill in with this region right here? 0.1, good. Now let's think about, what does that region represent? Is that region in A? But we put the 0.1, is that in A? Is it in B? No. So that's the intersection of what? What is that the intersection of? A and B prime, isn't it, right? It's the complement. It's the A and B complement, isn't it? It's in A, but it's not in B. So it's A and B complement, isn't it? Isn't that what they asked for in part B? Yeah. So sometimes the pictures help us think of those things, all right? We agree with that? Can I fill in this other little region inside of B? What's it going to be? 0.2? Because that's the part of B that's not in A, right? We agree with that? Okay. How much total? How much is in both of them now in the union? 0.6. Because notice now we've got it in 3 mutually exclusive regions. We can just add them together, right? A union B would be this region plus that region plus that region. We can do it this way too. And sometimes the pictures help, I think. There's one region we haven't labeled. What region didn't we label? Outside, right? If my rectangle is representing the entire sample space, I've got one more region, right? What number is going to go in there? 0.4, because why?
Has to be equal to 1.
Yeah, when you add everything up, I have to get to 1, right? The probability of the entire sample space has to be 1. We've already accounted for 0.6. So 0.4 has to make up the difference. That makes sense? Okay. The reason why I wanted to do this was because that last problem asked you for the probability of A complement union B complement, right? We could play around with the different formulas, but I think it's a little bit easier here to just look at it from the picture. I want things that are in A complement or in B complement, right? Let's go through the numbers. Let's do the easy one first. Is this an A complement or B complement? It's in both, isn't it? You agree?
Mm-hmm.
Okay. So this one's in there. That's one of the numbers we would want to add. Okay. How about this 0.1? What's it in? B complement, right? This is outside of B. This 0.2, it's an A complement, so we want to count that, right? I want 0.4 plus 0.1 plus 0.2 so far. Is this in there? Is this an A complement?
No.
No. Is it in B complement? No, because it's in both A and B at the same time, right? So one way we can look at this is that this would be 0.4 this stuff out here, right? And it's not in A and it's not in B. Point 1, that's not in B. Point 2, not in A. And I get point 7. That's one way to think about it, right? Another way to think about it is what's referred to as De Morgan's law. One of De Morgan's laws. Okay. How do I get not in A or not in B? Well, notice that the piece that we avoided was this one, isn't it? Notice that this part is the complement of what's in both of them, correct? So one of De Morgan's laws says that if you want the complement of the intersection, that's the union of the complements. It also works the other way. If you want the complement of a union, it's the intersection of the complements. These are what's referred to as De Morgan's laws. So again, think about it just in words that make sense. This is everything that's not in both at the same time. Well, if you're not in both at the same time, you're either not in A or you're not in B. Right? This is everything that's neither nor, right? Neither in A or in B. Not in A or B. So it's either, it has to be not in A and not in B at the same time. These are referred to as De Morgan's laws. We can use them to help simplify some things. But again, sometimes the pictures help too. That was why I wanted to make sure I did it with the pictures. This okay? All right. Let's see. Let's look at this, not the next one, but the one following it so we can play with some of the problems here. By the way, so a lot of these problems that are example problems I've taken from different actuarial exam problem review books, specifically for exam P for the cited actuary. So where a lot of these things come from. All right. So notice they give you a scenario here. Your probability of E is a half, of F is a half, and the intersection of the complements of E and F is a third. So it asks you to find one other one. So lots of different ways you might try to attack this. Let's just first try with the formulas. See what happens. Let's just start applying some formulas and see what we can do. So one of the formulas we had was probability of a union. How can I rewrite that? Just using the property that we had before, how can we rewrite that? Good. Yeah? Oh, don't we? Agree with that? This one's a half, and this one's a half. The trickier part is that part, isn't it? There's enough information to figure that out. By the way, what's typically true in most math problems that you do is that you use every piece of information you're given, right? The piece that we haven't used yet is that E complement intersect F complement. Let's go back to the picture I drew for the previous problem that we worked through and see if we can apply that same idea to this. Let's go back up here to my Venn diagram. We put in this 0.3 here because we knew the intersection of A and B, right? So this, but notice that there was another part of A that we didn't fill in, correct? This was A intersect B. This is A intersect B complement. We mentioned that, right? All together, we had to get A, didn't we? Okay. Let's go back over to now our problem that we're working on. We've got F complement here, don't we? This part is the intersection with E complement. This is the piece that we want, the intersection with E, isn't it? Altogether, what has to be true if I take this with this? What set do we end up with? If I take, let me say it a different way. If I take everything in F prime that's in E prime, and I take everything in F prime that's in E, what do I end up with if I put it all together? What set do I end up with? Let's put it that way. I end up with F prime, right? This is everything that's in F prime and E prime. This is everything that's in F prime and E, right? If I put the two together, I end up with F prime again, don't I? Okay. That's the same idea with the set. Let me draw the picture off to the side here real quick. Let's say this is E and this is F. So F prime is everything outside of F, isn't it? If I intersect that with E prime, that's everything outside the two circles, isn't it? If I do F prime intersected with E, that's that part, right? We agree? The outside part here was E prime intersect F prime. This part is F prime intersect E, isn't it? I get all of F prime, don't I? And they're mutually exclusive, correct? So our F prime is E prime intersect F prime union E intersect F prime, right? It's those two pieces together. What's our probability of F prime? Good, because probability of F was 1/2, right? What's your probability of E prime intersect F prime? 1/3. So what's this last probability going to have to equal? Good, yep, it's 1/2 minus 1/3, right? Because together they have to add up 1/2. These two things added together, when I take their probabilities, has to be 1/2, right? This is 1/3, so that makes up the rest of it. I have to do the subtraction of the two. What do we end up with? 5, 6 more done? Yes.
Now, if I'm
How problem is this? Okay. So this is my F. That's F prime is what I'm shading here. Okay. If I put my E in, which is here, this part would be, that's E prime intersect F prime. That's everything outside of E that intersects with what I just shaded. That's E intersect F prime. Because it's inside E and not F. All together, I've made up F prime. That's the picture help. Yeah. So that's how they're equal to each other. Basically what we're doing is we're just taking a set and splitting it into two pieces, right? Part of the set that overlaps another, part of the set that doesn't overlap the other. We'll do more problems like this on Thursday, as well as we get into section 1.2. So there should be a video on Moodle over methods of enumeration. So I'd like you to watch that for Thursday. I also want you to work on some homework. This is on page 10, problems 7, 9, and 14. When I want you to turn in problems, I always give you a week. So there's a class period in between. So this will be due next Tuesday, which is what, the 28th? Okay. Just those 3 problems. Okay? All right. Have a good one. I will see you on Thursday, if not before. I might see some of you tomorrow. If you're taking linear, you'll see me tomorrow. In here, as a matter of fact. All right.